Okay, so my name is Dietmar Hildenbrand. I'm from the University of Technology in Darmstadt, Germany. And I would like to present our tool GAALOP, which is able to visualize and geometric algebra and to generate optimized source code for different programming languages of these algorithms. So this is the agenda of my talk. I would like to introduce our tool GAALOP and its online version called GAALOPWeb. My focus will be on projective geometric algebra, which already Leo also presented. Then I would like to show you some examples how to deal with GAALOP. And at the end, I also would like to introduce some other geometric algebras, specifically the algebra for conics and the double conformal geometric algebra, because they are used later on in the session. For reference, I have a book published in 2013. It is a reference for GAALOP, our standalone tool specifically. And this is my third book. You can look into the two of my books here. This book is called The Power of Geometric Algebra Computing from this year, and this is dealing with the online version of GAALOP. Let's come to the standalone GAALOP in general. As I told you, it is a software in order to visualize geometric algebra, in order to compute with geometric algebra of arbitrary dimension and signature. And the main goal of GAALOP is to generate optimized source code for different programming languages. And GAALOP is freely downloadable from this from the webpage gaalop.de, and it is also open source on GitHub. This is the architecture of GAALOP. So at the top, we have our application described based on geometric algebra. And then we symbolically optimize the code. And then we can derive different implementations for different programming languages and are able to install them on very different devices. So for the description of our algorithms of geometric algebra, we have our specific language called GAALOP script. And from this, we generate some kind of intermediate language of optimized code. And then we support programming languages such as C, C++, C++, AMP, Julia. Chris will talk about also another implementation for Julia in the afternoon. OpenCL, Rust, MATLAB, Python, to mention only some of these possibilities. And then these algorithms, these implementations can be used for different computing devices from PC over GPUs, FPGAs, and so on. The main goal of GAALOP is to optimize not only specific multivectors, but complete geometric algorithms. Means it is not simply an API for geometric algebra, but it optimizes over many steps, and I will show you some examples in a minute. So our intention is first to pre-compute as much as possible before the runtime in order to have a very low amount of runtime then. And as I told you, we support very different programming languages from C also to, we have FPGA means a hardware solution, or some kind of mathematical software such as MATLAB, and also for new programming languages like Python, Julia, and so on. So GAALOP, in order to reach this goal, is a two-stages approach. So we first optimize simply the products of geometric algebra, and then in the second step, we optimize complete parts of algorithm. And this is supported by Maxima, a mathematical program in order to let us symbolically optimize our algorithms. The new version of GAALOP is called GAALOPWeb, and this provides an interface, a web interface, in order to deal with different geometric algebras. And the main benefit is that no installation is needed, and okay, we can support many different devices. Here's a list of some programming languages that we support: C++, Python, MATLAB, Mathematica, Julia, Rust, for example. And we also support many geometric algebras. So the 3D projective geometric algebra, which Leo presented, is our standard algebra, but we also support imaginary numbers, space-time algebra, for instance, the already mentioned conformal geometric algebra, the double conformal geometric algebra, and we also support geometric algebras dealing with quantum computing. So we support two of them. One is called quantum bit geometric algebra, Yaroslav will have a talk about, and the quantum register geometric algebra. Leo already mentioned the tool Ganja in order to visualize geometric algebra, and this is what we also use in our tool. Means our tool generates specific JavaScript implementations for Ganja in order to visualize. This is the main screen of GAALOPWeb. We have three windows: one to describe the code to optimize, one for variable assignments, and one in order to specify which multivectors should be visualized. We provide some quick help on the screen, as well as some sample GAALOP scripts in order to have a first basis in order to write your own GAALOP scripts. And we also have an introductional PDF in order to give you some information how to deal with this language GAALOP script, where I will show you some examples soon. What about the resources for PGA? Because I want to focus on PGA. I think Leo already mentioned a lot of them. The first is our GAALOP or GAALOPWeb homepage. Then the bivector homepage Leo already mentioned, as well as some tutorials about PGA. And the course notes of the SIGGRAPH 2019 of Charles Gunn and Stephen de Koenig. And then two very nice documents of Leo. One is a guided tour to the plane-based geometric algebra. And the other one is May the Fog Be With You, which is already mentioned. Oh, what I forgot is the course, the SIGGRAPH course of this year, done by Alan Rockwood and me. We have to think about how we can also provide this on the bivector.home page. Okay, what Charles Gunn and Stephen de Koenig did is to provide some cheat sheets for projective geometric algebra, and I think it is very nice to see that the main information of PGA can be put simply on one page. This is a structure of 3D PGA. In principle, 16 basic elements. One is the scalar, then the vector part, the bivector part, the trivector part. And in principle, this is already mentioned by Leo. Then we have the representations of planes, lines, and points. How does the laser pointer work? The middle? Okay. Okay, these are the 16 basis elements, and these are the representation of the objects which can be described in this algebra. Here you see the plane as the normal vector minus d times E0, the line as the intersection of two planes, and the point as the intersection of three planes. And then with GAALOPWeb, it is very easy to visualize the GAALOP scripts, and at the end we will also see how we can handle the rigid body example that Leo provided in his presentation. Here are some first steps for GAALOP script. So in principle, we always assign multivectors in each line. This is, for instance, the outer product. We can include some commands. The question mark means please explicitly compute this multivector. Colon means visualize it. And we can define different colors for the visualization. Okay, this is are the objects revisited. And here the first example. Here we define a plane defined by the normal vector E2, means in y direction, minus 0.25 times E0, means this is a plane with normal vector E2 and with a distance to the origin of 0.25. We say this plane should be yellow, and this means please visualize this plane. And what we also can see is the generated source code for this example. At the end, we have always 16-dimensional arrays describing our multivectors, and this is the source code for it. Okay, we only need 2 entries in this array. Only the E0, this is indicated by this command, the E0 component and the E2 component. And it is also possible, if we do not specify exactly what the distance is, then this distance is used in a slider, and you can play around with this slider or with this distance. Okay, here you can see an example of the intersection of 2 planes. P1 and P2 are the planes, and here you define the colors, for instance, and you can see also the green intersecting line. And if you intersect 3 planes, then they are defined as P1, P2, and P3, and then you can intersect simply by the again by the outer product. And if you would like to intersect the 3 spheres, this is simply the outer product of P1, P2, and P3. This is the generated C code. So you see only the entries of the array describing the multivector are defined, which are non-zero. As already Leo mentioned, we can meet and join 2 objects, and this is the join operator. And for instance, the join of 2 points, P1 and P2, means what is the line going through P1 and P2. And this is why we have, in principle, 2 representations. This one is already mentioned, and the other one is dual, means both are dual to each other, and we have a dual representation of the plane, which is a point. The line is dual to a line, the point is dual to a plane. And here you can see this is a definition of the point in this representation. And then having 1 point, the outer product means a line going to the 2 points, or for the plane, if you have 3 points, then the outer product of them is simply the plane going through these 3 points. So this is an example then for this join, means 2 points. The outer product describes the line going through it. Then the join of 3 points describes a plane. And if we make this f, let's go back. Here we have this f as a parameter, then we can play around with this f based on some slider and make some experiments. Sure, this is only a very simple example, but okay. I think I should skip this in order to come to a very important application that I would like to present. It is about transformations and motions. This is a part of the cheat sheet about that. You can see the rotators, translators, and you can also see how to deal with motions from one line to the other, from one plane to the other, what we need for the next application. It is also very easy to interpolate between planes. Here you can see 2 planes, and then based on this very simple operator, 1 plus the product of the 2 planes, you are able to interpolate between these 2 planes. So this is a simple linear interpolation, and then based on that, you simply can describe the interpolation between the 2 planes. And what I would like to present is how can we align 2 triangles. I like this example very much. It is also based on one document of Leo, and for that we define a so-called macro in GAALOP, because for the transformation from one point to the other, from one line to the other, and from one plane to the other, there is always the same computation. It is always this 1 plus first object, second object, and you already have the motor in order to transform one object to the other. It has also to be normalized, and then if you have your original points, these are the original points, and here we have an arbitrary transformation of it, and then the transformation is always described by the sandwich product, which was already presented by Leo. And this is the visualization of it. And how does this algorithm work? First, this is our original triangle. This is our target triangle. First, we translate 2 points, the A1 to the AT, and the algorithm is always the same. We always compute the motor based on this macro, make our transformation. This is for the first step. Then for the second step, these A's are already aligned. We look at these 2 lines here, this one, and transform one line to the other, again with the same functionality called motor, because in this is based on this motor. It is very simple to compute the transformation from this line to this line, and then again the corresponding transformation. And after this step, the 2 triangles are aligned in this way. And the only thing we have to do is to take the 2 planes of these 2 triangles and transform one to the other, and we have the final result. Again, we have to use the motor functionality and transform this plane to this plane, and then we have again a motor. If we compute the product of all these 3 motors, we have the complete transformation, and this transformation is describing how one triangle in space can be aligned to the other one. And sure, again, we can interpolate between them. Okay. And we can also deal with the dynamics. With the dynamics Leo mentioned in his presentation. And okay, this is a principal description of it. We already saw it by Leo, and we also saw this example. And it is very easy to take this example, convert it to these two macros in order to compute the next motor and the next velocity bivector, as Leo described. And based on that, it is very easy to generate optimized solver code of that functionality. Means this is a C code, but we could also provide Julia, Python, whatever code, if we have this very simple description of this dynamics. Okay, only to mention it, with this tool, it is also possible to deal with compass ruler algebra, which is a 2D version of conformal geometric algebra. For instance, in this case, we generate optimized Python code, or for the GA for conics, it is very easy to compute the intersection of an ellipse and a circle. This is how we can deal with a double conformal geometric algebra. Here we have a torus, ellipsoid, and a sphere, can visualize, can intersect, can reflect, transform, whatever. Oops. Okay, and coming to the conclusion, I hope I could convince you that this is a tool in order to simply develop GA algorithms, get feedback by the visualization, and generate optimized source code for different programming languages. Thank you very much.
So we have a question on the chat here saying, how is the geometric product implemented in GAALOP?
The geometric product implemented, did you say? So for very small geometric algebra, means with low dimension, we simply have product tables in order to speed up the compiling process. Means for the conformal geometric algebra, we have a table with 32 basis elements each, and multiply each of the basis elements, and this is the basis of the general product. Then, other questions?
Okay, so we have a few. Just one second.
So do you have a feel for how much faster GAALOP would be than something like Geigen for the double conformal model, just as a random example?
The principle of GAALOP is that it is not only optimizing products between multivectors, but complete algorithms or complete parts of algorithms. So we have the possibility in order to say, okay, please explicitly compute this multivector, but all the other multivectors are only intermediate values. And this is where the performance of GAALOP is coming from.
We have a question from Hamish
Yeah.
online.
Okay.
So we'll go ahead and give him permission to speak. Somehow. Is that what I did last time?
Thank you.
Hamish,
Hey,
got a question?
Hey, yeah, so I saw at some point in some of the code that was flashed on screen was you were multiplying, if I understand correctly, you were multiplying a motor by its dual. Does that sound familiar?
A motor with its dual.
Yes, I think so. Possibly, unless I'm misunderstanding the exclamation mark operator, is that the dual?
Oh, sorry. No, no. This
Oh, okay.
is only, please explicitly compute this multivector and use only the components that are needed further in the algorithm. So this is only an optimization.
Okay.
Something to show what kind of optimization should be done with this multivector. I'm sorry, I didn't have enough time to explain that. But
No, that's okay. So the exclamation mark operator was not the dual and was not. Yes,
no,
okay,
no.
Never mind. No worries. I'm just too used to seeing other people's notation.
Please compute this multivector. That's what it says in principle.